no ar.
Estamos? Ok, bom dia. Vamos dar prosseguimento ao ciclo de seminários do Observatório Nacional. Essa semana é um prazer apresentar a vocês um amigo e colaborador dentro da nossa colaboração do JPass, Tam. Ele é o atual diretor do Observatório de Tartu, na Estônia. Terminou o doutorado em 2006, após umas passagens pela Universidade de Göttingen, no Instituto de Astrofísica de Canárias, Valência. Virou pesquisador titular, virou pesquisador no Observatório de Tartu e atualmente pesquisador titular. Desde 2018 ele é professor associado da Universidade de Tartu e agora, como eu mencionei, ele é o atual diretor. Ele também é o líder do grupo do JPass da Estônia, que entrou na nossa colaboração há vários anos atrás, tem sido extremamente produtivos e com vários projetos interessantes. A área principal dele é a formação e evolução de galáxias, estruturas de galáxias, propriedades de matéria escura, e mais recentemente tem trabalhado na distribuição de matéria escura na estrutura em larga escala do universo. O Observatório de Tartu tem vários pesquisadores famosos na área de superaglomerados, que é o que ele vai falar hoje, incluindo a Inasto e outras colaborações com o N, inclusive na parte de estrelas com POEMS. E ele vai falar um pouco sobre aglomerados no JPass e talvez mostrar o observatório para a gente e outras coisas interessantes. Então, sem demorar mais, vou passar a palavra para o Antti. Antti, you have the word. Everything I said about you was good and true.
Thank you, Renato. Hello, everybody. I hope you can hear me.
Yeah.
So, I am Antti Tam. Right now I'm in front of my workplace. So behind me is the Tartu Observatory. I will switch the camera, perhaps you see better. So this observatory is it's on the top of the mountain. Renato has seen the mountain. It is 100 meters from the sea level. For us, it's a proper mountain. It started as an astronomical observatory, but now we have other fields of cosmic research as well. So we have, in addition to looking into the sky from the Earth, so in addition to astronomy, we have also looking down from the sky to the Earth, which is called remote sensing. So remote sensing of water bodies, of forests, of farmlands, using satellite data, airplane data, all these things. And then the newest topic here is actually space technology. So from here you can perhaps see we have some satellite communication antennas on the top of the building. So in principle, we have all space research in one center in Estonia, which is actually very useful. We have also some telescopes. You won't see them from here, they're a bit farther away. Along this path. We have some exhibitions also for the general public who come to visit us. And while you are still, I guess you are still waking up. And for me, it's already the end of the working day. So, and we also, right today, we concluded the academic year. So we have an event actually going on. You can see some people. It's 4 p.m. So we're finishing the working day already. So I try to wake you up with a scene. And here you can also see some of our JPass colleagues, those who know JPass. You can see, you can meet.
Morning.
Jan Laur. We have Juhan Liivamägi. You will be hearing about them during the talk as well. Let me see. Let me see. I think no more JPass people right now. So let's go inside. So as I said, we have space technology. I will show you a bit of the labs. We have labs for electronics. So this one is electronics lab. We have a nice rainbow on the wall by chance. This is one of the space technology labs. Here we have testing systems for small satellites. So we have a vibration bench right in the middle of the screen. We have a shock test bench to simulate rocket, the separation of rocket, what are the stages, yes. And then behind this clean room door, we have more systems for thermal vacuum testing and some optical calibration and testing facilities. So we can in principle do all the things needed for putting together and testing a small satellite in our own building. And actually there is one satellite still flying, which was produced here by students a few years ago. It's not operating anymore, but it did a good job for a few years. You can see this small satellite, the CUBE satellite, 10 by 10 by 10 centimeters. So it made good pictures of the Earth and carried out some experiments. But the main topic here, maybe which is most well known, has been the studies of large-scale structure of the universe, and I will be telling mostly about this today. And of course, the large-scale structure consists of galaxies, like this Andromeda. And here is a mosaic of pictures made by this small satellite of the Earth. Okay, so now I will walk into my office and switch over to my computer. And sorry for the suit, I had this event. Normally I'm not dressed that up. So let me just now switch over to the other screen. And hello again.
Thank you for the tour.
I hope you can still hear me.
It was great.
Okay. So I will be telling you about superclusters and the link between JPass and superclusters. And I'm, of course, not working on this alone. Actually, because of my directorship, I have quite few time for science right now. So we have a list of colleagues. Elmo Tempel is the most active. He is a professor of astronomy, and he has done most of the coding of the engines of our different structure detection algorithms. Jaan Laur, whom you saw downstairs, he is our most active participant in JPass, who does redshift determination algorithm testing, and I'll be showing most of his work today. Juhan Liivamägi, he is our supercluster guy. So he has been focusing on supercluster detection and analysis methods. And I also listed here Maret Einasto, who is also focused on supercluster analysis, and our grand old man, Jaan Einasto, the father of Mother Einasto, by the way. And Jaan Einasto is 93 by now, but he's still active. He still comes to the observatory and he's still publishing first author papers. So it's a good example for all of us here. And in the background, this is our observatory from above. And it is part of Tartu University. So Tartu is a town 20 kilometers from the observatory. And where we are actually, so while you have, I guess, something like winter approaching, then we here have summer approaching. And if I figured out correctly, at the mirroring our latitude to the southern hemisphere, we would be somewhere between the Argentine and the Antarctica. So quite far in the cold zone. But right now we have quite warm weather, 23, 24 degrees. So in this talk, I would try to discuss defining the superclusters, then talk about how to detect superclusters, how to use superclusters for cosmology, if they can be used at all. Then I will peek into possibilities of using JPAS for detecting superclusters, and a bit more technically about our aims of measuring best redshifts for JPAS with a custom-made algorithm. But why all this structure detection? So I think it's about mapping the universe. And one reason is that we don't want that there is too many of such regions in the universe where we have to write that here be dragons, which we don't know about. So we want to cover all these most remote and most dense, most devoid regions with observations, so that we know more about them and also what they are telling us. And here in Tartu Observatory, it all started quite some time ago. Here is a historic reminder of a conference held in 1977 in Tallinn, in the capital of Estonia, entitled The Large-Scale Structure of the Universe. And in this photo, you can see Jim Peebles, George Abel, Malcolm Longyear, and Jaan Einasto discussing the large-scale structure. And remember, this was just a little bit less than a decade before surveys like this one. I don't know if you can see the mouse, but I can turn it larger. Sorry.
We can see it.
So now it's better, I guess. So before such surveys of redshift data came out, where you really could see these large-scale structures, at first, of course, they appeared a bit suspicious. Why did they look like human beings? But you could already see that there is a pattern of voids and filaments and denser regions between them. And the other reason, apart from just mapping the universe, is that actually it's a very embarrassing situation for cosmologists, at least for me. Whenever I need to explain to the public, to school children or other interested people or the funding agencies, that what do we know about the universe? And then you have to show this figure. at 73% of the universe, we have no idea about the dark energy. 23%, we have just speculations what is dark matter. And only this small 5% sector is something that we know about. So this situation is rather embarrassing, and despite all the efforts that have been made to detect dark matter particles, for example, underground in space, or measure dark energy, some parameters, we have had no real success, and we still have to find ways of saying something about these two mysterious topics. So perhaps we can use superclusters as one probe. So in astrophysics, we have quite much exhausted the microscale detections in particles. So, and also average scales, let's say galaxy level. But at the largest scales, perhaps the patterns of the universe can tell us something about either dark energy or dark matter more. So what are superclusters? One thing to say, of course, is that superclusters are not, as often thought, large clusters. So a galaxy cluster, like this one, this is something which has a high density contrast with respect to the average of the universe. So it's a dense region. It is gravitationally bound by definition. So all of its objects, they cannot escape anymore the potential well. It is also virialized, meaning that the velocities with which the galaxies move, they correspond to the mass of the whole system. So if you imagine when you place these galaxies into the system without any velocity, at some point they start to collapse. They gain velocities and then they become virialized. Their velocities will characterize the total mass of the system. So this is virialized. And galaxy clusters usually are pretty well virialized. Not always, but pretty well. Also, you can say that they are detached from the Hubble flow. So the universe is expanding. And of course, because of this big gravitational potential, they don't follow this expansion. They are forming a stable system. They have been detached from the Hubble flow. And they contain, a galaxy cluster contains one cluster. Whereas a supercluster, in general, it's a low density region in the universe. The average density is not more than a few times higher than the average of the universe. And it is not bound gravitationally, so it is not a cluster which is bound. Instead, it consists of may consist of several up to tens of clusters, even big clusters, also groups, smaller and larger groups, and filaments in between them. And even sometimes you can count voids, some smaller voids being parts of a supercluster. And superclusters, in general, they are not detached from the Hubble flow. So they are expanding together with the universe, although maybe they could be expanding a little slower, and in some regions they might be already collapsing. I will touch that a bit later as well. And this example here is a Laniakea supercluster. So it's a rather recent discovery or definition. So this is our own local supercluster, probably you have heard. And then this is our largest home, which we can think of. How was this Laniakea supercluster defined? This was done by Brent Tully and his colleagues in 2014. And he used very delicate way to delineate this structure. So instead of just using the positions of galaxies, he also had data about the actual velocities of the galaxies. So in the local universe, you can do this up to within some limitations, of course. So once you have all the positions and the velocities, you can fast forward and see where would these trajectories that the galaxies currently have, where would they lead? And this way you would find that within some regions, all the sources, they would end up in a single point eventually, if you switch off the Hubble flow, the expansion of the universe. And in the neighboring structures, they would end up in different separate points. So thereby you can determine something like watersheds between different structures, along which then galaxies flow into towards one attractor in one side and towards another attractor on the other side. So this was Brent Tully's definition for a supercluster. And pretty straightforward. And you can see this dot represents the "you are here" place. This is our Milky Way, and we're quite in the suburbs of the Laniakea. There are some problems with this kind of definition, of course. First problem is that you can only do really for the local universe, where you can really measure the proper motions of the galaxies. The second problem is that if you define superclusters this way, you actually you separate the whole universe into superclusters. So superclusters are bordering other superclusters. You split the universe into spheres of influence. And I personally have a problem with the spheres of influence. So before the Second World War, Germany and Soviet Russia, they divided Eastern Europe into spheres of influence. So some countries being in the influence zone of the USSR and the others to be part of Germany, or the sphere of influence of Germany. And we all know where it led to. Eventually, Russia and Germany, they conquered Poland, and eventually when Poland was conquered, then they, on the watershed, the officers from both sides, they greeted each other as friends. Well, and then the rest of the history happened. So I don't like very much this kind of watershed-based or sphere of influence-based distribution. Instead, we use luminosity density field. So what is this? This is where our Juhan Liivamägi is an expert. You take the distribution of galaxies, just the coordinates, and you smooth them with a kernel. Thereby you create a luminosity density field, taking into account the coordinates of each source as well as each luminosity. And if you want to do it really correctly, then you compensate somehow the Malcolm bias, whereby more remote galaxies tend to be, you see only fewer of them, only the brighter ones, but you can compensate for these. You know how this functionally, this luminosity is decreasing, what you observe. So you can compensate for that. And thereby you get a uniform representation of structures all over the observed field. We have been doing this for mostly Sloan Digital Sky Survey data, also the BOSS survey, also for simulations, the Horizon simulation, one of the largest ones done in Korea. And we would very much like to try it on JPAS data. And what could we do with such information? We could, for example, this luminosity density field, it could be quite simply, not very precisely, but quite simply be turned into stellar mass density field. And given the huge volume and high redshifts expected from the JPAS data, we could study the evolution of the mass density field from, let's say, redshift 0.1 until now. So really cosmological distances. So how do you define then galaxy superclusters from these density fields? So in these figures, this plane represents the X and Y coordinates, or the sky coordinates, and then the brightness of the source is along the third axis. So when you start to map the structures from the highest contrast points, you start from these mountain tops on the figure. First, to detect at the highest contrast levels, to detect these very tips of the mass concentrations. And then you come down to lower contrast levels, you detect more of these mountain tops. At some levels, they start to merge, forming larger structures, but some structures still remain separate. And you can see this well on this merger tree-like graph. So first, at the highest contrast level, you detect this first cluster, supercluster center. Then you detect the next ones. And at some point, they start to merge. And then you define some level at which you say that, okay, now we have finished supercluster detection at this level, and these structures which are still separate, they are different superclusters. Or you can actually define also different levels for different structures. So you can define that for this structure, we finish the threshold lowering at this level, but for another structure, you can go deeper. And this this means that there is actually no straightforward way how you define a supercluster. It depends on your goal of science, as well as on the data that you have. So, for example, if you, for Sloan-like data where you don't expect much cosmological evolution, you can set the criterion that I want to have roughly the same density of superclusters in the local sample and in a more distant sample. Then you need to have a different contrast definition. And here is an example. What would then the universe look like? So I hope you can see it. Every color cloud represents a different supercluster in this Sloan Digital Sky Survey volume. And you see they don't cover the whole volume. So superclusters do not border with other superclusters. There are still huge voids between them. And this way, at least the term cluster is more well preserved than in the case when you use this dynamical approach, where the whole universe is built up of clusters only, superclusters. So what about the cosmology? How can you use such detections of huge systems for testing cosmology? So one argument or one idea comes from the fact that there are actually some quite huge structures detected. The first historically and the largest one so far is the so-called Sloan Great Wall. So in the Sloan's data again, it's very apparent when you look at the distribution in the sky of this slice. There is a very high concentration of actually clusters and superclusters. And suspiciously, actually, it is in the tangential or sky plane coordinates when observed from where we are. So the first idea is that, oh, perhaps this is some kind of cosmological effect. It's not a real system. To some extent, this is true. So then there are these, for example, Kaiser effect, which comes from the fact that sources moving towards this mass concentration, they appear differently in this redshift plot than they would in real coordinates. But considering this huge volume of this system, it's still real. But is it correct to consider it to be a single structure? This is a matter of debate. It consists of several superclusters, and you can define it as you wish. The total extent of this structure is around 420 megaparsecs over age. So it's a really dominant thing in our local universe. The Sloan Great Wall. Then there is also the BOSS Great Wall, detected by my colleagues in the BOSS data. These BOSS data are then the more distant sources in the Sloan survey, the luminous red galaxies. And then these data showed an interesting structure of 4 separate superclusters, which form also a single-like item. So in total, 830 Sloan galaxies, and the size scale is 300 megaparsecs. So if you think that the Sloan Great Wall is perhaps not a single structure, then this one would be the largest known so far. But it's somewhat subjective. And on the lower plot, you can see the individual cores, the central regions of each of the member superclusters of the system. Actually, funnily, this huge structure, it has also inspired artists. So there is a sculpture actually, and other forms of arts made on the basis of this distribution of galaxies in the Sloan Great Wall structure. Most recently, there has been also detection of another large system called the Saraswati Supercluster in the same Sloan data at about redshift 0.28, so a bit closer than the BOSS Great Wall, and of a slightly smaller scale. So the question that might be intriguing is that are such huge systems actually corresponding to the cosmological model that we have? Would you get such structures out of simulations as well? So at first, it was not very clear. Sorry. First, here is a list of from Wikipedia, the list of largest structures. So you can see structures being detected also by other methods like gamma ray bursts, also from quasar data, but quasar data are pretty sparse so far. But you can see all these that we have mentioned, the Sloan Great Wall, the BOSS Great Wall, and even the Laniakea supercluster among the top 20 of the largest systems known in the universe. So why bother with these things? If we think that, okay, our theoretical picture, which we feed into simulations, does it represent similar structures? Then actually the problem is that the number statistics is rather low. If you have just one single or 3 single huge structures, then if you have a large enough simulation, or you repeat the simulation with different conditions for many times, eventually you will have such structures, of course. And here are some examples. So this work made by our Korean colleagues, it shows on the left panel is the actual observations, and on the right panel are the simulation data of both superclusters on the left and the voids to the right. So these guys, they looked for the largest superclusters and the largest void systems in the data, as well as in the simulations, to see if they roughly correspond to each other. And indeed, you can find that the physical scales over a few hundred megaparsecs for clusters and perhaps a bit more for voids. They are quite similar in simulations as well as in observations. And also the visual impression is pretty much similar. So this hope that superclusters, the very existence of superclusters in the data tells us that we have a problem in the cosmology was not true. However, when you do more careful statistics about the actual richness of these structures and the actual size distributions, then the results are not very clear. So there is somewhat debate. There is no consensus whether the statistical factors, they are similar in observations and in simulations. And the main problem is that the samples are not large enough. We need larger redshift surveys. So here is where JPAS is much wanted. We are waiting for a data set where we can cover a much larger volume of the universe. And if you have heard, probably you have heard too much already about JPAS, but the JPAS target accuracy of redshifts at an average redshift of let's say half, 0.5, the target redshift would be around 10 megaparsecs. So not a very good accuracy for redshifts or distant measurements. So if you consider a normal galaxy cluster is of the scale of 1 to 3 megaparsecs, then putting together clusters takes some effort. But for superclusters, which extend to around 100 megaparsecs, this actually is not an issue, especially when you consider that it's just not a linear error of 10 megaparsec, it's a Gaussian distribution. So you have more galaxies which are less off from the true value of the redshift than those which are actually 10 megaparsecs off. So no big problem for supercluster detection. However, we're still waiting for mock data, for simulation data, which simulates the JPAS structures as well as the redshift distributions to assess this question quantitatively. Is it really not a problem to accurately detect superclusters? So this mock construction is on the way in the JPAS collaboration. What else you can do actually with superclusters? You can study them individually. And this is one example. This was since we were having Corona season, and we studied the Corona Borealis supercluster. So a supercluster in the constellation towards the constellation of Corona Borealis. And when you have a luminosity density field, you can transfer it into mass density field. And from there, you can actually calculate the acceleration field of the region. So this supercluster field, I don't know if you can see, these lines are pretty hard to see, but these vectors, they show this acceleration field, and you can determine what is the current and future dynamics of this system. And on this right-hand panel, you can see with the blue circle, this is the radius of turnaround. So here, the supercluster has, or the structure has detached from the Hubble flow. It's not expanding. It's already collapsing. With the light blue, this larger circle, this shows where the galaxies are still expanding with the universe, but slowing down. And eventually they would also be collapsing. So currently they're still moving away from each other, but they will collapse in the future. So such dynamical studies you can conduct with individual superclusters. But when you have more of these systems in the data, then you can actually do already statistical studies at local distances, at cosmologically interesting distances, and compare when and where do systems collapse and in which timescales. And now we get to JPAS. So I'm not going into detail about JPAS campaign and the facilities. Just very briefly again that the main idea is that we have a large number of narrowband filters which we can use for spectroscopic like observations on this JPAS main telescope with a huge CCD, so you can see the comparison with the credit card of the CCD. So really massive, and we have great expectations for this instrument. And I don't know well about the audience, so I will very briefly also describe what is cosmological redshift actually, so and how do we measure it. So if you imagine a galaxy having a spectrum, let's say a blue spectrum like this one, or a redder spectrum like this one, in the local universe or in its rest frame. And now when you put it into redshift at redshift 0.5, then this galaxy is flying away from us, so that we see like the Doppler shift, but this is cosmologically caused redshift, and all the spectrum is shifted towards redder colors. And if you see that the scale is not linear, it's logarithmic, then also actually this distribution is stretched out. So every wavelength is pushed, is multiplied by a factor, and thereby pushed redder. And at redshift 1.5, you would already have the same galaxies without any blue colors. And now we have to do the reverse exercise. We have to guess what is the actual spectrum of the object, and then find which redshift corresponds best to this observed spectrum. So this brings us to photometric redshifts. So since even if we have 60 different filters, this is still not a spectroscopic redshift. It's still not a real spectrum. It's still a photometric measurement. And therefore, it's still photometric redshift exercise. So there are many different ways of measuring these photometric redshifts. But in a nutshell, they are pretty similar in the way that they all use galaxy colors or the whole spectrum. So here in this example, there are different colors. There can be very many colors. And you find for each set of colors, you find the best matching redshift. Having a guess about the original spectrum or the template of the source. Also considering, of course, the transmission of the filters and all the other optical effects. So you can do the same exercise with machine learning. You just teach your system that these spectra, they correspond to these redshifts, and those other spectra, they correspond to other redshifts. Or you can do simple template fitting, you template matching. You take all your templates, different spectral templates, and then you shift them along the redshift and find where does which template match the best. So for this, you need, of course, input photometry. You take the templates, you compare them to the input photometry, and you do the comparison between the model and the data. And thereby you get the distribution of or probability density distribution for the redshifts. And in this way, this is if you do it in a Bayesian way, you can also introduce some priors. You actually have some more knowledge than just these observational data. You actually know that, for example, very bright galaxy cannot be very far. They are more likely to be nearby galaxies. So this is prior information. You can also guess that galaxies with very red colors, they are more likely to be distant and so on. So you can add such prior information and you can adjust this probability density distribution. And then you can validate your data using either spectroscopic data or some other external data. And then you have your redshift distributions as well as some best estimates for the redshifts. So this is photometric redshift estimation principles as of 2021, as we have now. Currently, the JPAS survey has not yet started, the full survey. We still have the mini JPAS data. And the mini JPAS data, while they are pretty much similar to the, hopefully, to the eventual JPAS data, or even slightly worse, the redshift distribution is pretty good. It covers up to redshift 1, although at 1 there are very few galaxies already, and the magnitudes from anything around 17, 18 down to 22.5, 23 in AB. So in this area, you can do your testing and calibration of the redshift estimations. What we did, we wrote our own code for redshift estimation. Although there is plenty of codes existing already, we did our own custom-made code for the JPAS so that we can take all the JPAS effects into account concerning filter, transmissions, and so on. So time is running out, so I will speed up a bit. So we have our set of templates. We compare the set of templates to each galaxy photometry or J spectrum, and we find where are the matches the best. And from these, you get these redshift density peak values. And actually, how to determine which is the best estimate. For example, in this case, which is shown here, you have many peaks. So actually, it's not so straightforward to say that, I think my galaxy is here on this redshift or here. So we have different definitions for the best estimate. But wherever possible, it's the best to use the whole distribution of the redshift. I'll skip some of these examples and just a bit about some things that we found during our exercise. So the effect of prior. So we just simply used this luminosity-based prior, and we found that when we don't have the prior, for example, in this upper panel, the galaxy redshift distribution is the gray one. And actually, the peak value is not where is the spectroscopic redshift estimate. However, when we take the prior into account, the distribution is corrected so that the peak value is exactly where it is supposed to be. Very good. However, we have also exactly the opposite cases. So original distribution again is gray, and we have a good peak where the spectroscopic redshift estimate is, but after introducing the prior information, this peak is suppressed and the wrong peak bumps up. So it's not so straightforward. And we did some other tests. It's interesting that actually the number, how many templates you are using for testing your galaxies, it has a peak value at which your redshift estimates will be the best. And this peak value actually depends on the galaxy brightness. So fainter galaxies, they would prefer less templates, while brighter galaxies, we have found funnily that around 100 templates gives the best estimate. But in general, our results were pretty online with the JPAS target accuracy. So the photometric redshift corresponds quite well to the spectroscopic one. And the redshift error distribution is quite Gaussian, but there is an interesting phenomenon which is still not clear and also found in other redshift with other redshift algorithms on JPass data that the maximum is not in the center. So we tend to have slightly higher redshifts in our photometric estimates than are the true values. But once you know this, you can actually correct, you can just simply shift slightly the redshifts and you get better precision. So here this 36.1 shows how big percentage is in the redshift target limit, within the error limit of the JPass survey, and 14% are the outliers, which are catastrophic failures. So we think we're so far doing pretty well. There is still ways of improvement. And then especially for the main JPass survey, when we have many more galaxies with spectroscopic counterparts, we can fine-tune our estimators. So with this optimistic note, I will say obrigado, and you are welcome to visit us here in Tartu.
Thanks, Antti. That was very, very interesting. Let me see here. Simone, you have, let's see, I cannot see hands or things like that. I don't know if you have.
Yes, I will I will promote the Wenderty and Carlos Galarza. They have questions. Just a second.
Hello, can I ask you? Or...
Yes, go ahead.
Okay. Thank you, Professor Ante, for the interesting talk. Yeah, it was very, very nice. I just wanted to know how do you go from map, like you computed the 2D map on the sky, and then you go to something like the luminosity and you make the measurement. It's basically, I would like to understand better how do you measure the supercluster? How do you can you measure it? I guess it was in the beginning or something like that.
Let's start from here.
Yeah, that one.
So this is actually a slice of the 3D distribution, right?
Mm-hmm.
One slice. We are here at 0, and these are on the outer radii. They are the most distant galaxies, and this is one slice. So actually, you have a 3D distribution instead of this slice.
Mm-hmm.
And then, well, in practice, we have we go into X, Y, and Z coordinates, and then we work on this grid of X, Y, and Z to calculate these luminosity density fields, and then start doing these threshold exercises.
I see.
There are a few corrections on the way, actually. So one is this luminosity correction, so that we remove this effect, which you can see on this upper panel, where you have fewer galaxies farther away and more galaxies nearby. These fewer galaxies, they are these most brightest ones only. But when you do this luminosity density field, you can compensate for this, knowing that actually galaxies have quite similar luminosity functions. So we have a similar number of bright and faint galaxies in the outer regions as well as nearby. So you can compensate for these effects. You cannot do it for just the galaxy distribution because you don't know where to place these extra galaxies. But when you are smoothing the things, then it's not that critical anymore. So this is one thing. Then actually what we have done more before we go into these levels, we also correct for, I don't have a plot. Maybe on here you can see there's the fingers of God. These galaxy clusters, they are stretched out. So actually what we have running below the surface is galaxy cluster detection. We detect the galaxy clusters, then we suppress these fingers of God. We know that this is a cluster, and we place it in the central coordinate of the system. So thereby we get rid of these fake filament kind of things, and then we do this supercluster detection. In case of the JPAS data, actually, this is not so critical, this finger of God effect, because our redshifts are spread out anyway by the error.
So yeah, thank you. So you need to have the 3D map. I thought it was a 2D only. Yeah, but
high coordinates and the redshift. This is why we are also working on the redshifts.
Yeah, makes sense. Yeah, I have another question. You said that this can be used as a probe, a cosmological probe. So what kind of constraint do you expect this probe to deliver? Like how this would be compared to other probes nowadays, how they can, could they, multi-probe analysis combined with other kind of probes?
Well, let's say it's, you have, at larger scales, you can use other probes as well. You can use correlation function, for example. But I'm not actually very sure whether correlation function, so this is a correlation between galaxy pairs. So how, at which scales you have how many pairs. And at these large scales, you start already to have very many side effects, which you need very, very well to take into account to do a proper correlation function analysis. So the hope is that perhaps at these scales, these hundreds of megaparsecs, you can actually do better with supercluster statistics. So we have actually, what I didn't show at all, you can also characterize the superclusters by different parameters about the shape, about the mass distribution, and so on. So you can check how well these parameters are reproduced in simulations. So the simple or naive question is, do you get similar distributions of any parameters in the simulations as you get in observations? And if you don't get, then you have the question that, okay, let's see, is it a result of different cosmology, or is it something that you just don't understand?
Yeah, that was my other question. Why don't you use a two-point correlation function to detect this?
Yeah, two-point correlation function is also used, and three-point correlation function is even better in this aspect. You also get the shapes. But of course, it is a very slow process. And you have very many effects where you have missing data and so on. And side,
yeah. Thank you.
Thank you.
Carlos, do you have questions too?
Yes. Can you hear me?
Yes, very well.
Okay. Thank you very much, Professor Antti, for this talk. Well, and I initially I had just one question, but listening to the previous one, now I have two questions. And since I'm not from the cosmological or extragalactic field, I just will focus on some details you explained in your talk. The first question was regarding the luminosity function to study superclusters. This luminosity function is based on a specific filter of Sloan or a composition of the filters?
So you mean which data we are using from the Sloan?
Yes. To calculate the luminosity function in the plot.
So you mean this luminosity density field? Or luminosity function for correcting the luminosity?
Well, the one that you show in the previous question there. I don't know. I don't remember the figure, but you showed that like the slow when you presented the Sloan the Sloan plot to study superclusters.
Yeah, I think it must have been. Wasn't it this one?
I'm not. I know. I didn't see the slides. I can't see the slides.
You can't see the slide now?
No.
Oh.
I don't know.
Somehow the screen sharing stopped.
Yeah, that one.
Okay. So this was from Sloan R filter, if I remember correctly.
R filter. Okay.
Yeah.
Okay.
Because you could use also I in principle would be more favorable, but I has some is not so accurate in Sloan, so there have been issues.
So in this case, the best filter to use probably is the R.
Yeah, it depends on the actual data set that you are using, but yeah, you wouldn't want to go bluer than R, definitely, because then you are missing the so you would detect other things than you're trying to trace the mass of galaxies in principle, right? And the redder you are, the better.
Yeah.
And also you can go more distant with the R and I.
Yeah.
Mm-hmm.
Okay, thank you. So the other question is also, well, very specific. In the end of your talk, you were explaining some things calculating regarding estimation of photometrical redshift. Well, I saw that this estimation is like in the lower. Well, I don't know if it's correct to say that, but to me it's like in the lower redshift range. So is it possible? Have you tested this on higher redshifts, or is it possible to estimate higher redshifts with JPass or data? Or
yeah, of course, at higher redshifts you have only the brightest sources, and in the currently available data, which is this mini JPass field, beyond redshift 1, you have like a handful of galaxies only. So it's very difficult to say anything. But in principle, yeah, especially quasars and luminous red galaxies, you can say something about, or some specific emission line galaxies. But just the numbers are currently very, very, very small. So
yeah, I think it's because it's a matter of we don't have enough data or enough reliable objects. I mean, I guess.
Actually, again, this is a place where much depends on your focus. So if you are focused on more higher redshifts, then we should tune our algorithm. We should choose different templates. We should choose different priors, many things, and then you get better results. But for this, we need some data to tune to use for the basis of tuning.
Yes, I know. Mm-hmm. Your point is completely right. So maybe because it's interesting to me how the code should. Imagine that we have some like hidden object that we don't know. The code works well for the bulk of data, but there is some like hidden objects that how the code should process those objects. I mean, if you try this code that is well tuned to this range of redshifts, but maybe there are some outlier out there that has higher redshift, how the code should, how the code will process that object.
So the problem really is, that you can. One of the reasons for outliers is especially for emission line galaxies that you think the algorithm thinks that it has found the line, but actually it's some other line. And if you have just one line detected, then this error is quite easy to come, and then you have out completely off from the real redshift. But and you cannot really do anything about it. But just what you can do. So for every single source, it is very hard to tell what is the real redshift. You have some distribution, but the good thing is that actually you can get an estimate about the precision. So you would know that actually how much for which sources you are missing. Then you can for cosmological applications you can take it into account, and also the best case is when you can take the whole distribution into account. That okay, I don't know the exact redshift for this galaxy, but I have 10 million galaxies, and when I sum up all these distributions, I get the real redshift distributions very, very accurately. So this, for the statistical purposes, this is very, very good.
Sure.
But then this is a big challenge actually, which is under discussion in JPass, that how to present these distributions. So it's much more data needed than just for a single estimate, this peak value. And then also processing when you're analyzing, then it's very time consuming, computer consuming.
Sure.
Yeah.
Yeah.
But yeah, for every single object, it is very hard to tell how good is your estimate.
Okay. Thank you very much.
Any other question?
I actually had one question for Antti. So Antti, I thought it was very interesting. You were basically delineating some of the difficulties that might have with the definition of supercluster, and the way that you are going to go about cosmological parameters would be by cross correlation, by correlation functions, and so on. And I was just puzzling, I mean, naively thinking that perhaps you could do a simpler job by using voids instead of superclusters, doing the other way around. But then, from what I understand, and you can clarify this much better, but you're going to have the same kind of difficulty in defining at what point one void is separated from the other, because you're going to have this kind of similar structures that elongate spatially. And then I went back to thinking that perhaps supercluster would be better, because even though JPass has this limited redshift precision, it's very good, but limited at 0.5. It says about 10 megaparsecs and so on. The tests so far with mini JPass in the clusters group found that we actually can get a significant number of very small groups. It gets 1 times 10 to the 13, some even smaller than that. Even though the number is small, because we only have mini JPass. It's for how can I say, it's actually doing what it was promised to do, of getting very low mass systems for the first time in this intermediate redshifts, at least. And so if you have at least a few galaxies with a precision of, say, 900 kilometers per second, right, 0.3%, not the majority, you can still, through scaling relations, tell the mass of the system, and the system is there. And therefore, you can trace this the supercluster to a larger extent. So I was wondering if that is how much of an advantage this is, and if there is any correlation between the number of clusters and distribution between clusters and groups, or mass distribution for superclusters, that actually is reliable so far.
So actually, I think there is a whole avenue of possibilities to tune the data better by the fact that we know that here is a supercluster, here is a cluster, here is a group, and this you can say that this is like a prior for redshift estimates. So knowing that there is a cluster around here, this raises the chances of a galaxy which is on the same line of sight to be in this redshift range. So you can actually raise the precision quite a lot if you have some structures.
Mm-hmm.
Yeah, I don't know if this answers the question, but I think, yeah, there is a high potential of much higher than this seemingly bad 10 megaparsec precision to detect structures and to. But the problem is, that how well you can assess really for example, if you want to estimate the shapes, then all these 10 megaparsec spreadings, they have an effect on your shape detection and these other parameters. So this is an issue. But you can say that here is a structure. But in my vision, it's with Bayesian redshifts and Bayesian cluster estimation, for example, or Bayesian supercluster estimation, you can improve the precision of both quite well.
Right.
But not again for any single object.
Yeah. And a kind of iterative process, right?
Yeah.
Yeah. Okay.
No, actually, there is no need for iteration. You just raise the chances for both. That you know that here is a redshift concentration, this means that redshifts are more likely in this region. Should be more likely. You don't need to iterate.
Okay, thank you. So one just probing intuition, everybody. So there's a slightly, you showed a slight tendency to get the average redshift a little bit higher. I think by maybe 300 kilometers per second is the average from your plot, something like that. Do you have any guess so far of what is causing this? Even though the systematic can be corrected, I don't know if you have any guess of why this is being consistent throughout all the different Photo-Z codes.
We have a few tests in our minds, but one thing could be that this is first time when the filters are so narrow. So this is first time that the spectra are probed in such high density, right? So actually we have no earlier experience how the codes work in these regimes. And then just one blind guess that I have had is that when you imagine that the galaxy spectrum, it's not flat, it's always tilted somewhat. And maybe you somehow probe this tilt. It introduces some offset in your luminosities when you model this transmission through this particular filter. So it's a bit, yeah, it was a bit vague, but for example, yeah. So there can be or interaction with lines, although I think we were shown that the same effect is for galaxies with emission lines and without emission lines. So it's not an effect of lines. But we have some ideas in our minds. But it needs some more testing.
Okay. Okay, thank you.
It seems Wendert has another question, or you just forgot?
Yeah.
Okay.
If I may. Well, you're saying, Professor, that you are detecting really huge structure, like this huge, like the Coronavirus wall, I guess, and also this Sloan Great Wall. This is like 400, I guess, and megaparsec, and also between 2,000 and 3,000 megaparsec for the Coronavirus gamma ray burst wall. So I'd like to hear from you what do you think? Is this supercluster would mean a puzzle for the cosmological principle?
And not by itself probably, but the question is, can this, if we assume that all the structures they are seeded by original Gaussian random fields, then is it realistic that you get these scales? But in principle, of course, yeah, the Big Bang universe does not limit the scales. So
this, if you actually detect such a structure, it doesn't mean that the cosmological principle is violated?
Not in itself, no, not this way. It's not the cosmological principle. It's not yeah, it's not causally connected, I guess. Yeah.
Yeah.
And still it's not clear. So it's a debate. Is it just a random enhancement of density that you can from the statistical Gaussian field you would get these anyway if you have large enough sample. This is one possibility. So it's a bit under debate.
Yeah, so it doesn't directly mean that the cosmological principle is violated only because you have like a 3,000 megaparsec structure. So it can happen even its cosmological principle holds.
Well, so between us, I can say that some of these large structures which are detected with different methods where you have quite few objects, then these are statistically not very meaningful. So if you say that you have a huge structure based on 30 objects, there are such papers, then you know.
Yeah. Thanks.
Okay. So Simone, are there any more questions from your side?
I think no. I think from, let me check the YouTube. No, there is no question there. And yeah, I think no.
All right. Okay, so let's thank again Antti. Tom, take the time. It's last day of work, right? You're starting the vacations there now.
Yeah, we have vacation season starting. Yeah.
So to present this fantastic talk to us, and hopefully we can visit each other and when things get a little better.
Yeah, thanks for inviting.
Thank you very much. And see, now you can go back to to your party. That's great.
Thank you.
Bye-bye.
Bye-bye.
Bye-bye.